All right, today we're going to pull back the curtain on a really clever bit of cryptographic magic. It's a key piece of tech in things like Bitcoin, and it's called a Schnorr signature. And what it does is solve a very, very old problem.
So let's start with the puzzle. How do you prove you know a secret without actually revealing what it is? Like proving you have the password without ever showing it to anyone. This is the classic secret keeper's dilemma, and it's the exact challenge we're going to solve today.
Well, the solution is something called an identification protocol. And really, the best way to wrap your head around it is to think of it like a digital secret handshake. It's this structured back and forth, a conversation, that's designed purely to prove you know something.
So, if we're going to get a little more formal, an identification protocol is just a method where one person, the prover, can show another person, the verifier, that they know a secret. The prover proves, the verifier verifies. Pretty straightforward, right? But to make this crystal clear, let's bring in our favorite duo from the world of crypto. Okay, so meet Alice and Bob. Alice is our prover. She's the one with the secret. And Bob, he's our verifier. Let's just say he's a little skeptical. He needs proof. But the whole point is Alice can't just show him the secret. So that's the challenge they're facing.
All right, so here's the game. Alice has to convince Bob that she knows her secret private key. We'll just call it X. And the number one rule is X can never, ever be revealed. So how in the world does she do it? Well, it all comes down to this really clever, almost choreographed conversation.
Okay, let's walk through this dance. Step 1. Alice makes a commitment. She picks a totally random number. Let's call it K, just for this one-time chat. She uses K to create a public point R and sends that over to Bob. You can think of this as her, locking in her first move. She can't change it later. Step 2, Bob throws down a challenge. He just sends a completely random number, we'll call it E, right back to Alice. Now, this is the crucial part. Step 3, Alice has to respond. And here's where the magic happens. She takes her temporary random number, K, Bob's random challenge, E, and her super secret private key, X, and she combines them all to calculate a response, which we'll call S. She sends that final number, S, to Bob, and now Bob has all the pieces he needs.
Okay, so Bob's got everything he needs, and now he does the final check using this really elegant little equation. I know, it might look like a jumble of letters at first, but trust me, this is where the whole trick comes together. He takes Alice's final number S, her first move R, his own challenge E, and Alice's public key P, and he plugs them all in. And if the left side equals the right side, if the equation balances, it's game over. It proves Alice knows the secret. The math is it's beautiful. And here's why it works. This is the big reveal, the ta-da moment. See, when Bob plugs in all the numbers, what he's really doing is unwrapping Alice's calculation. Because psi is actually K plus E times X, the whole thing just magically rearranges itself. The only way, and I mean the only way, for that equation to balance is if Alice used the correct secret key X to create her response. It's a mathematical lock that you just can't pick. You can't fake it. So you might be thinking, okay, but why can't Alice just cheat? Great question. And the answer is all about the timing. Remember how she had to send R first? She's committed. She can't change her mind. Only after that does Bob send his totally random, unpredictable challenge E. Because she can't possibly guess what E's going to be, there's no way for her to cook up a fake answer in advance. The only path to a balanced equation is by actually knowing the secret X. Okay, so this whole back and forth between Alice and Bob is really cool, right? But it's just the beginning. The really clever part is that you can take this whole conversation and turn it into a static, digital signature. Basically, instead of Bob providing a random challenge, the challenge is kind of self-generated from the message being signed. This means you get a single piece of data, a signature, that anyone can check later, without ever having to talk to Alice. So, why all this fuss? What's the big deal? What's the killer feature of Schnorr signatures? Well, it comes down to one word: multi-signatures, or multisig for short. This is the ability to have multiple people, a whole group, collectively sign a single thing, like a transaction. And the way Schnorr does it is just unbelievably efficient and private. All right, so let's dig into why this is such a game changer in the real world, especially for tech that really needs top-notch security and efficiency. So let's do a little compare and contrast. The old way of doing multisig, the legacy way, it was kind of clunky. If you had, say, 3 people signing something, you'd literally have to put all 3 of their public keys and all 3 of their signatures on the blockchain. It's big, it takes up a lot of space, and worse, it screams, hey look, 3 people signed this. Not great for privacy. But with Schnorr, oh man, those same 3 people can work together behind the scenes to create one public key and one signature. And from the outside, it looks exactly like a normal single-person signature. It's way smaller, which means it's cheaper, and it's a massive win for privacy. And this, right here, is the revolutionary idea. It literally doesn't matter if it's just one person signing or 10 people signing. The final result on-chain is just one key, one signature. That's it. All that complexity, all the details of who is involved, it all gets rolled up and hidden inside this one simple, elegant proof.
And look, this isn't just some abstract idea on a whiteboard. This is real, and it's being used. This technology was the absolute cornerstone of the Taproot upgrade in Bitcoin. It's what's enabling much more complex and much more private transactions on the network today. It's out there in the wild, making things more efficient and protecting people's privacy right now.
So, let's leave you with this final thought to chew on. When a signature from one person and a signature from 10 people look completely identical, when you can't tell the difference between a simple payment and a complex multi-party agreement just by looking at it, what kind of new possibilities does that open up for privacy? It's a really powerful concept, and it all comes from that simple secret keeper's magic trick we just unpacked.